Daniel's talk. Daniel comes to us from CWI in Amsterdam, not Idaho. And he is, I think, yeah, I mean, it's hard to find words to describe the fantastic research that Daniel has done. I mean, he's spanned theoretical computer science, integer programming, convex geometry, probability theory. He's just one of the stars in our field, I would say. He won, for example, the Tucker Prize from the Mathematical Optimization Society. He recently won a huge grant, which is like in the millions of euros from the European Research Council, with which he's going to
pay for lunch.
Oh, yeah. and pay for lunch, yes, that's right. So it's a great pleasure for me to introduce Daniel. He's going to talk to us today about, I think, linear programming, but that doesn't appear in the title, so I may be mistaken. Go ahead, Daniel.
All right, yeah, thank you very much for the introduction and for having me here. So I'm going to talk to you about a specific algorithm for linear programming. So indeed, the linear programming will be the subject. And we're going to essentially learn about let's say, a condition measure of linear programs that probably you are not familiar with, and that I think is sort of very interesting to study more deeply. Yeah, so we'll get to it. And this is a joint work with my students, Sophie Halberts and Bento Natura and Lassie Beck at LSE. Okay. So we want to solve linear programming, and in this talk we're always going to be interested in solving the problem exactly. So when we solve a linear program, I'm going to want exact primal and dual solutions. So this is just a primal and dual pair, starting from a linear program in standard form. Yeah, maybe many talks in linear programming that you might see are sort of okay, you know, with approximate solutions, which I mean, in some sense, changes the problem or the game quite a bit. So maybe, you know, some of the results that you will see later will seem sort of less impressive because our running times are terrible. But you start seeing, let's say, different facets of the combinatorics when you want to solve the problem exactly. Okay. And so, of course, yeah, lots of people have thought about linear programming. Yeah, it's probably difficult to kind of, you know, overstate the impact that the search for, you know, new, faster, different algorithms for linear programming has had on optimization and computer science. So, I mean, I'm not going to dwell too much on the history, but the, let's say, environment that I want to put this talk into is related, again, to this question of how difficult is it to solve linear programs exactly. And one way of thinking about that question is in the context of the difference between strongly polynomial algorithms and weakly polynomial algorithms. And as you'll see, the strongly polynomial has this not terribly good definition. So I think it's still up for debate. But you know, morally, when people were thinking about combinatorial problems that are special cases of linear programs, you're thinking about flows and problems of that type. And for such problems, usually you expect, or with some work, people were able to show algorithms that solve certain types of min cost and max flow problems exactly in time that only depends, on the number of edges and the number of nodes in the graph. But when you go to linear programming, suddenly ugly things happen, like the number of iterations of your method starts to take time that's proportional to, the bit complexity of the description of the problem, which I guess from the combinatorial side seems, very, very unnatural. And so the question was if you can find, an algorithm that somehow maybe it needs to, add and multiply or maybe divide, large numbers together. So that kind of witnesses a little bit the complexity of the fact that your input is given to you with horrible numbers in it, but you kind of want the number of iterations of the algorithm to be to only depend on the design dimension of the problem. Okay, so more formally, you have the following distinction. So weakly polynomial, if you have n variables and constraints, and the encoding length of your input is L, you're happy with a running time that depends polynomially, where let's say the number of basic operations that your algorithm performs will be allowed to be polynomial in the bit description length. However, you try and sort of extract away what like a nice algorithm should look like, and this is one such abstraction that I think maybe Grosha, Vavasis, and Schreiber have in their book. I will say that I'm not like a super huge fan of how this is sometimes abstracted, because like basic arithmetic operations, if you sort of look at what people might write down, they will say something like, we're happy with addition, we're happy with multiplication, but we're like not happy, we're happy with addition, we're happy with multiplication, but we're not happy with division, which seems very strange for most normal people, because division, it's sort of, you can't obviously do it in sort of in a time that is reasonable in this model. So I think there is room to like improve what this model should really mean, but morally, these are the like natural algorithms that people who do combinatorics would like to see. So something like a simplex method is what people have been looking for a long time. That would somehow iterate over the vertices and edges using only a polynomial number of pivots. We obviously haven't found one. And these are the nasty algorithms like the ellipsoid method. Okay. Good. So actually, maybe one more thing I want to say about this. So this is like one framing of the question. In some sense, what this talk will more be about is about how to appropriately measure the complexity of solving LPs exactly. So if I give you an LP, I want to be able to stare at it and come up with some let's say intrinsic measure that tells you how difficult it should be to solve the problem. And this can come in sort of many different forms. So if people are familiar with the ellipsoid method for solving feasibility, if you have a polytope and you happen to know that okay, somehow it's bounded, so it's contained inside some ball, and you know that the volume of the polytope is large. If the volume of the polytope is sort of not too small compared is not too small compared to the volume of the containing ball. So maybe this is the ball that contains it. Then you can find a point inside this polytope, in time that's sort of proportional to some log of the ratio of these things. And that would be, one geometric measure of how difficult it is to find an exactly feasible point inside this polytope. But of course, if the polytope has zero volume, because it's a lower dimensional polytope, which is, in essence, if you take an optimization problem and reduce it to a feasibility problem, you will always have something lower dimensional. So you have to look at sort of more interesting things than this. Okay. And that's what the talk will be about.
So just to clarify, when you say you want to solve the LP exactly, are you going to look at the feasibility version, or you want a pair of primal and dual solutions?
It'll be a pair of primal and dual solutions in this case, yeah. So yes, we will solve the optimization. So again, you know, the sort of history of this in some sense is a lot of the kind of search for you know, let's say combinatorial-like algorithms for LP was influenced by the work on network flows, which is all classical. You know, these kind of nice algorithms have been extended to special classes of linear programming. So I think the person who sort of first tried to let's say formalize, or well, at least ask the question in on paper, and Bill, you can correct me if I'm wrong. I think Megiddo is the one who defined sort of, he didn't call it strongly polynomial, he called it genuinely polynomial or something like this. So showing that if you have a feasibility system where every row has at most sort of 2 non-zeros, you can find a feasible solution in strongly polynomial time. You have things based on generalized versions of flow, which sort of were resolved quite recently, and special types of Markov decision processes. And there's more on this list. But of course, we're very far away from getting these types of results for you know, very, very large classes of LPs. Okay. So good. So what we're going to be interested in today is something about solving a general LP. And what we're going to look at is we're going to look at conditions that make the LP easier to solve that only stare at the constraint matrix. Okay, so we're not going to care about, we're going to try and abstract away the coefficients of the objective and of the right-hand side. So in particular, you know, a notion like volume of the feasible region cannot work in this setting, because I could always like change the right-hand side so that the polytope is infeasible, or lower dimensional by moving the constraints around. So it's really going to be, you know, it's a step towards trying to get nicer algorithms, staring at the complexity only of the constraint matrix. And here there are essentially 2 main results. One of which is, I think, relatively well known, and the other is less well known. And the less well known one is what we'll be discussing more about today. This was a breakthrough result of Eva Tardos, and essentially she took her work on minimum cost flow and realized that it sort of generalizes to arbitrary LPs. If you assume that the data of the constraint matrix is integral, this is actually a very serious assumption in this particular context. And then if you look at every square submatrix of A, its determinant is upper bounded by delta. Okay. So, I mean, a special class of LPs of this form are, which many, I'm sure you have seen, is where if delta is 1, these are totally unimodular constraint matrices, which appear, of course, all over the place in combinatorial optimization. So this was generalizing, in some sense, on that. And so in this context, she showed that you can take the parameter of the constraint matrix, if it's integral, to basically be the maximum subdeterminant. Okay, that was what you could show. Actually, sorry, this should be log delta. Yeah, my bad. And less sort of well-known, but also a serious sort of breakthrough result, is due to Ye and I think Stephen Vavasis. And what Tardos did is actually, it turns out, is a black box result. So it sort of says, if you give me any weakly polynomial algorithm for solving LPs with small integers, then I will repeatedly apply this algorithm on sort of rounded versions of the objective and the right-hand side to eventually find an exact optimal solution to your problem. So this is actually a black box reduction to being able to solve LPs with nice coefficients. Whereas this paper essentially gives a single interior point method, which doesn't, it's not a black box anything, and it's a very specific method, and it solves the problem in one shot. And it also works, and this is kind of a rather non-trivial extension, for any matrix A, in the sense that it doesn't depend in any essential way on the data being integral. So that's yeah, that was sort of a major breakthrough. And it depends on this parameter which you see here, which is chi bar of A. Okay, and I would say probably 90% of this talk will be convincing you that this parameter is very interesting, and you know, I mean, it has been studied extensively, but we will see more reasons to study it in this talk. Okay, so let's try and talk about this parameter that they depend on, and then we'll see a little bit of how this fits into the context of interior point methods and where we improve things. So I want to first give you just a sense of what this parameter measures. It turns out that there are many, many, many different definitions, and some of them are far scarier than others. So this is possibly the simplest definition one can give that is maybe somewhat intuitive. What it says, or what it tries to measure, is essentially if, so here is perhaps a slightly useful example. So assume, so I'm going to measure something just that is measuring the complexity of the kernel of the matrix A. So it's like the complexity of a linear subspace associated with A. In this case, it's the kernel. And what it tries to say is like, okay, assume I know that, you know, if I have a partial vector, 1, 2, right? And I know that I can lift it so I can set these coefficients so that it lives in the kernel. Okay, so currently this vector 1, 2 is in the projection of the kernel onto the first two coefficients. Okay, so that's why I have 1, 2, star, star. I know that there is some way of filling in these two stars so that I can make it live in the kernel. And the question is, like, how expensive is it like, how big are these coefficients going to be in terms of the starting coefficients? Okay. So the parameter is essentially defined to say that the moment I know that I can lift this partial vector to live inside the kernel, then there is going to be a lifting that is somehow small with respect to the input, right? And this small is measured in terms of, you know, the norm of the lifted vector is at most some number m times the norm of the input, okay? And this, you do this for every subset of coordinates. So here I just did it for the first two coordinates, but you could do it for, you know, any subset of size 1, 2, 3, 4, sort of whatever you want. And if you have a bound for this like lifting cost over all subsets, that, or the best possible bound you can get, that is chi bar of A.
So is there any way to check that this condition is met given?
No. I mean, sorry, yes, but it's NPR. I mean, essentially, okay, it turns out that if you give me the subset you want to start with, if you tell me, like, what is the lifting cost from the first two coefficients, then it's an operator norm. a matrix that is easy to compute, we'll actually sort of explicitly see it. But the issue is that I don't know which subset, and there are exponentially many subsets. And it turns out that you can restrict to subsets that are of size equal to the dimension of the subspace. Like you don't actually need to go higher than that. So this is the kind of starting definition. We will see later like a much nicer combinatorial version of this, which in some sense makes it easier to reason about. But importantly, okay, so this is the measure that Vavasis and Ye depend on. And when I was mentioning that it's sort of a non-trivial extension asking the algorithm for the algorithm to not depend on the integrality of A, like as Tardos' algorithm is written, or her reduction is written, it cannot depend on this. This is too stringent or it's too small of a parameter for Tardos' algorithm. I mean, there are versions of it that would work, but it's substantially more complicated. So, okay, firstly, one notices that this is something about only a subspace. So it's something that only depends on the kernel of A. So you give me any matrix that has the same kernel, it'll be the same number. And you can say some sort of very nice things about it. It's always sort of upper bounded by, the bit encoding length or 2 to the bit encoding length of the matrix, so it sort of fits in to, I mean, essentially if you have a parameter of a matrix that is not of this size, something has gone seriously wrong. So the bit encoding length should always be something super pessimistic, and okay, in that case at least this is. You can see that if you start, for example, with like a network matrix, then this parameter, okay, it's not 1 in this definition, but it's like something like square root of n. Like in essence, like if I, you can think of, if I have like I mean, roughly speaking, the problem is, if I have like some number of edges of a cycle and I want to complete it to a cycle, that would be in the kernel of such a network matrix. Then I only need to set some coefficients over here to 1 and others to 0, and that will complete the cycle and put you inside the kernel. So somehow the cost that you pay to lift the other coefficients is very small compared to the input. And this also generalizes to any other vector you would put in here.
So for totally unimodular matrices, this is small.
Yes. Yes. So this is like a better measure, or it's it sort of captures the benefits of T units. Yeah, I think that's the right way of putting it. So it is very related to things you know, and you'll actually see in another version of this, which we'll talk about later, that the relationship is even better. Okay. And yeah, in terms of the question of can you check whether this parameter is small, so horrible things, you can't even get this kind of approximation back. So if you want to approximate how big this quantity is, essentially because you have to enumerate over all possible subsets, you essentially cannot get any reasonable approximation that only depends on the size. This is the, like it really should be like 2 to basically any computable function is essentially not possible. Okay. So now we're going to talk about let's say, yes, the object of interest that we will, or that can be analyzed. So we won't actually say a huge amount about how the analysis goes in this talk. But the object of interest is going to be the central path, and we're thinking of the kind of standard version of the central path that uses the standard logarithmic barrier for an LP. so if you have the kind of standard form, which I forgot to rewrite down, do I have it? Yes. So we have a standard form LP like this. Okay. Then the central path can actually be defined sort of very simply in the following way. It basically says, so this is your primal, this is the slack in the dual. Forget about y. Y turns out to be not so interesting. And essentially what you want is the sort of product of the primal slack and dual slack should always equal a fixed mu. And as you scale mu down to 0, you will essentially be moving along this path until you get to opt. So this is only tracing the picture in the primal, but a similar picture will occur. You'll actually have two curves, sort of, let's say the primal curve, which is x, and the dual curve, and they will both tend towards optimal solutions. Okay. And what will happen, or what happens in this paper of Vavasis and Ye, is that essentially what they show is that if you if you can initialize properly, so there's some non-trivial annoyance with initialization, so you get anywhere on the path. What you're trying to do is to get to the end. And what they can show is that literally you can follow the entire path all the way until the end in a number of iterations that is exactly this n to the 3.5 times log of chi-bar.
By all the way to the end, you mean actually to the vertex, because
Yes.
not an epsilon.
Exactly. It's really they follow the entire path, and if it goes into the if it's optimized into the middle of the face, I mean it's not going to get the exact limit point. So if it's a vertex, you'll get exactly the vertex. But if the optimal solution is the entire face, it'll get somewhere close to the analytic center of the face, but it will follow the entire path. So this is. We're really measuring the complexity not of moving along the path for some amount of time. It's like we want to actually, cover the entire length. All right. So this chi-bar parameter, if you use the right steps of the interior point method, you will be able to follow the entire path. Okay.
So it's not like with other interior point methods where you actually have to do a rounding step at the end to get to the vertex. Assume that there's a unique vertex.
Yes. So essentially, what will happen is that a generalization of the rounding step becomes one of the steps of the method. That's what happens, and that's in essence. So I didn't stress it in the previous slide, but I said they have a step that's called the layered least squares step. And that is exactly a generalization of what the rounding step would be, but that you actually do all over the place. You don't just do it at the end. Okay. So this is the object that we want to study. So this parameter chi-bar. So there is an open question, which is somewhere in this slide, and which is, essentially the main thing that we will resolve is the parameter that we looked at. This chi-bar turns out to be not scaling invariant. And what kind of scalings are we talking about? We're talking about scalings that correspond to sort of diagonal scalings of A, which means in this case, I'm scaling columns of A up and down just by positive numbers. Okay? And this actually just corresponds to scaling the kernel by a diagonal transformation. It's just, so it's really a diagonal transformation of the kernel. And what happens is that there is a sense in which the normal interior point methods that do not follow the Vavasis and Ye scheme have the same symmetries as the central path itself. So the central path that I wrote before, there is a very easy correspondence. So if I start from my matrix A, so if I start from the data of the problem and I scale everything appropriately by this diagonal transformation, then the central path transforms in a completely kind of formulaic way. Okay, so essentially, no interesting property of the central path is changed by diagonal scalings of the columns or scalings of the columns. So if you have a central path point in the original problem, this is the new central path point at that parameter in the transform problem. And if you look at interior point methods that, I mean, I guess like many of you may have seen in classes on linear programming, they're all invariant under this. So if you start the interior point method at a specific point, and then you just scale everything in this way, the method will do the same thing. If you run it in the other space and scale it back, or if you run it in the starting space. So that's a nice property of these methods. Now the Vavasis and Ye algorithm, it turns out, is not. And you don't have to pay too much attention, but mainly the reason is that they use information about how the variables are ordered in terms of size. So if you look at the primal variables, I will like order them, let's say, in decreasing order of size. And like obviously, if my method is supposed to be invariant under scaling the variables up and down by arbitrary amounts, the variable ordering information cannot be preserved by, so if I scale this one down by 1/1,000,000 and scale this one and up by 1,000,000, obviously that's going to change or can change the variable order, which means that the method itself is not invariant under the notion of symmetry, I mean the standard symmetries that methods are usually invariant under. And so what is the implication of this? So if, yeah, the algorithm was sort of appropriately invariant under rescalings, then what would happen is that the running time of the method would actually not depend on chi-bar of your matrix A, but would in fact depend on chi-bar of the best possible diagonal scaling of your matrix A. Okay. Now, I mean, one of the issues with this type of thing is that, you know, already like the chi-bar of A looks like a scary thing. And then now you're trying to understand, like, what is chi-bar of the best possible diagonal scaling of the matrix? Like, this seems like completely hopeless to understand. So there is hope. This is you know, this is important. But good. So if one could come up with a version of the Vavasis and Ye algorithm that is invariant under the sort of natural symmetries of the LP, you would have this kind of dependence on the complexity to follow the central path until the end, as opposed to just a dependence on chi-bar. So this chi-bar star is what encodes the optimization over